Okay. So last week we nearly finished with all the mechanisms of the reactions that we are going to meet. And we discussed this diagram. We have discussed all sorts of nucleophilic substitution reactions. The only thing that we have left out was part of the elimination reaction we didn't finish. And we were talking about the elimination of alcohols and also of halogen alkanes. So we spoke about the alcohols, but we left the halogen alkanes. So perhaps let us say that the last part of these reactions that we need to know the mechanisms, that is. And then we can discuss about various organic groups together. So, okay, last week we discussed the elimination of alcohols, which we also call dehydration, because what really happens is removing one molecule of water from the formula of an alcohol. That is why it's called dehydration in the case of alcohols. And how was this happening? We had the catalyst concentrated phosphoric acid or sulfuric acid, doesn't matter. And what happened was that the proton from the acid would be attracted to this electrons, a pair of electrons from the oxygen of the hydroxyl group, of the hydroxide here, and would form this intermediate positive the oxygen would be left with a positive charge, which means that a pair of electrons from this bond would move to the oxygen, and this whole portion here would be eliminated as water, that hence the dehydration of the alcohol. And on top of it, apart from that, since this pair of electrons moved to oxygen, obviously another pair of electrons would move to this bond between the carbon-carbon atoms, and this hydrogen proton would be eliminated as proton. And here we can see the whole of the products. The result would be the formation of this alkene plus the water that left the initial alcohol, and this proton, which means that the initial input of from the acid is regenerated, and that is why this acid is behaving as a catalyst, because really it does not participate. The hydrogen from the acid that helped this dehydration actually was produced at the end through the elimination of this, through this knockout of this other hydrogen up there, because this bond ends up as a double bond between the two carbon atoms, resulting in the alkene produced. So the result of this dehydration was the product of an alkene plus a molecule of water plus the hydrogen that the proton rather, that is part of the acid that helped this reaction. So that was the moral of the story from the elimination of alcohols. But now let us move on to the elimination as it appears in the halogen alkanes. And to have an elimination reaction, and here is an example of a halogen alkane, a bromoethane, we need to react it with something like what is this? Potassium hydroxide or even sodium hydroxide, because it is this hydroxide, due to this hydroxide, that will happen. But these hydroxides must be in a solution with ethanol. With ethanol, it's called an ethanolic sodium or ethanolic potassium hydroxide. Because if the solution is not ethanol, but it's water, instead of having an elimination reaction, we are going to have actually what is a nucleophilic substitution rather than elimination reaction. So it makes a difference what type of solution we have to, and therefore, in particular, to have an elimination reaction of a halogenoalkane, we have to dissolve one of these hydroxides in ethanol, in alcohol, in ethanol. Or else we will not have elimination reaction. We'll have nucleophilic substitution. Okay, so what happens now? It is this hydroxyl that will cause the elimination. What happens now is that the hydroxide ion, this hydroxide ion acts as a base, and by acting as a base means it removes the proton from it removes the proton from the carbon atom next to the carbon that is connected to with a halogen, with a bromine in this case. So this, in other words, will attract this hydrogen, and at the same time, a pair of electrons that form the covalent bond between the carbon and the removed proton form a double bond between the two carbon atoms. So, in other words, at the same time, this pair of electrons forms a double bond between those two carbon atoms, and the carbon bromine bond breaks. And so that is the third thing that happens here. So the first step is that the hydroxide ion acts as a base and removes one proton from but be careful, this proton that is removed is from the carbon atom which is next to the carbon atom linked to the bromine atom here. So from here, this is the removal of the proton, and therefore this pair of electrons now becomes a double bond between the two carbons. And once the two carbons here double bond, which is the second step, the third step is that this pair of electrons moves to bromine, and what is the result? We end up with a bromide ion. So this one breaks away. So if what are the products actually? Remember here we have a double bond, so there we have a double bond, and the remaining, of course, are hydrogens now, because the bromine atom here left with the pair of electrons here, so we have now plus obviously this became a water molecule, and we have now this bromide ion that was paired. Obviously, this bromide ion, depending on what we have used, what kind of base we used here, which hydroxide, potassium or sodium, that will come out in the form of either this salt or the potassium salt, potassium bromide or sodium bromide, depending on what we used. So this is the mechanism of that corresponds to the elimination of a halogenoalkane. So that was a halogenoalkane, and the result is we end up with an alkene with a removal of one water and of course the bromide ion. So there's but be careful. The important aspect here to remember is that in order for this elimination reaction to occur, our hydroxide that we use must be dissolved in ethanol, not water, because if this was dissolved in water instead of alcohol, we would not have an elimination reaction. We would have a nucleophilic substitution. Okay, and the product would be, of course, an alcohol. Okay. now that we have finished with the elimination reactions, the two elimination reactions of interest in our case is so here we have the elimination reactions. We are ready actually to start discussing the reactions of various groups of organic compounds, like let's write them. For example, the alkanes in general, the alkanes, all the alkanes which belong to these categories, indeed, saturated organic compounds. In fact, what? In fact, alkanes are hydrocarbons. Okay, so alkanes, we can see that being saturated can undergo either can undergo substitution reactions and also elimination reactions, apart from the combustion reaction, of course, that or the oxidation reactions that can happen to all the organic compounds. But in terms of us knowing the mechanisms of the particular reaction that they undergo, are the substitution and the elimination reactions. Now, alkanes in particular undergo combustion reactions, which can be either complete or incomplete, depending on how much oxygen we have available in which they burn. And if they are complete, they produce carbon dioxide and water. If they are incomplete, they would produce carbon monoxide and water. But these we do not have to know any mechanism. We just need to know how to write the reaction. So that is why we do not have the combustion reactions under these types of reactions here. However, the alkanes now can undergo substitution reactions. Okay, substitution. But what type of substitution reaction? Substitution reactions they can undergo the free radical substitution. Okay, free radical, because alkanes are very highly unreactive because they are saturated, so they don't need to react. But nevertheless, the free radicals, if they are available, they force them to react, and they undergo substitution reactions. Now, so in other words, for alkanes, we need to know that they undergo combustion reactions and substitution reactions in terms of this free radical. These free radical substitutions are particular to the alkanes. Now, what else? What other important group of organic compounds we have? We have the alkenes, which are unsaturated alkenes. Here they are, unsaturated hydrocarbons, alkenes. So since they are unsaturated, they can undergo primarily addition reactions, electrophilic addition reactions, apart from the oxidation reactions that they can undergo. Where oxidation reactions, we don't need to know any mechanism, we just need to know how to write the reactions, oxidation. So I'm just making a summary of the various reactions that we can meet in the various groups of organic compounds. So oxidation reactions, which is not part of these three reactions of which we need to know the mechanism. Okay, then but they can also undergo, of course, addition reactions, and this is where we need to know the mechanism, and we have discussed all these mechanisms. Addition, how do you spell? Addition reactions. And in furthermore, the very important reactions that the alkenes can undergo is the polymerization. Polymerization, again, it's not part of these reactions that we have discussed, because it's not about knowing a mechanism. It's simply, but hold it, let me write it first. Addition, polymerization. So in other words, they are the root of the polymers, very, very important compounds in organic chemistry. The polymers happen through the polymerization of the alkenes, addition polymerization, because there is another type of polymerization, but you need to know this addition polymerization. And we're going to discuss that separately, okay? Although this does not involve any special mechanism involving this curly arrow, so that is why we haven't not discussed it up to now, and that is why it does not appear here. But nevertheless, that's a very important type of reactions, and we're going to discuss them in the near future. Next group of important group of organic compounds, of course, is the halogen alkanes. Now, the halogen alkanes actually belong to this category of saturated organic compounds, which are not hydrocarbons because they have one of the hydrogens has been replaced by some other compound, the halogen in our case. That is, in this case, that's why we call them halogen alkanes. They are also called haloalkanes. And nevertheless, let us stick to the same name in the book, halogen alkanes. Halogen alkanes. And being part of these saturated organic compounds, as we can see, they can undergo both substitution reactions and elimination reactions, apart from other reactions that we do not need to know the mechanism. So substitution and elimination reactions. So substitution, and elimination. In fact, we just spoke about the elimination reactions of halogen alkanes now. For substitution, we have done all the substitution possibilities of halogen alkanes, which they can react either with the hydroxide ion or the cyanide, and also apart from this negatively charged groups, they can also react with molecules like an ammonia molecule, and we discussed how this reaction takes place, the substitution reaction. Very important, and perhaps this, be careful because it's a little bit more complex than the others. Anyway, and what elimination, what have I written here? Elimination, goodness. Elimination reactions, okay. Then we come to this category that I want us to start thinking today already, where we have, well, this chapter in the book that is entitled Alcohols, Esters, and carboxylic acids. Carboxylic acids. Why do they have this together? Because actually all these are very closely linked, because if an alcohol reacts with a carboxylic acid, produces an ester in the process that we call esterification, a very important aspect. And I would like us to talk about this esterification now. But nevertheless, now alcohols, alcohols, if we go back to this diagram again, we're going to discuss about the alcohols that belong to this category here, this saturated organic compounds. And therefore, we are going to see that alcohols can undergo substitution reaction and elimination reactions, which we call dehydration, because in alcohols we remove one molecule of water, so therefore it's a dehydration. So in other words, under alcohols, we see that we are going to find a number of reactions, and of course combustion reactions, okay, combustion reactions, of course. Then, of course, substitution reactions, they undergo substitution, reactions, and they also react with sodium or reactive metals. The esterification, very, very important, esterification. They undergo esterification reaction, which can be also called condensation reaction, but let's stick to esterification. Of course, they can go on elimination reactions because they belong to this category. Elimination reactions, elimination, which in the case of the alcohol we call dehydration. Dehydration is the same thing. And lastly, we're going to see oxidation reactions. Oxidation, which means they react with oxygen, because in the oxidation and reduction reactions in organic chemistry represented either with a gain of an oxygen, or in the reduction is corresponds with a gain of a hydrogen, but the reduction actually concerns the carboxylic acids mostly. But nevertheless, we are going to see all that. But since we have time today, I would like us to start from this esterification, which is actually a reaction from is the result, the product, when an alcohol and the carboxylic acid react together. But for this, I have a video to show you. Let me find the video. I hope we have enough time to see it. Okay. And an alcohol, methanol. Both of them the simplest acid and the simplest alcohol from the organic compound. If the two react, what happens is that from the acid, the hydrogen of the acid and the hydroxide combine and produce water, and what is left is a product that we call an ester. And which ester is going to form here? How are we going to write this ester? Since the hydrogen here and the hydroxide here combine, this remains the same. So I write this as it is, with carbon and oxygen there, the carbon with hydrogen here, and the oxygen and the other oxygen. And here, this part now connects with this methyl, with this alkyl. So that will be this methyl substituent. So this product now is called an ester. In fact, we can also write it in this form, why not? So this part here is the part that comes from the alcohol, and this part here is the one that remains from the acid, from acid. And how do we name this product, which we said already is an ester? What type of ester exactly is that? First in the name, we use this part from the alcohol. So this is methyl, and then what remains from this positive ion from the acid, methyl. What is there from the methanol acid? The methanol with a suffix that corresponds to an ester, methanoate. So methanoate, and that is the name of this ester that is formed from this reaction. Now this reaction, which reaction from organic chemistry does it remind us? We have an acid, actually, we have an acid and a base, really. And what is the product of an acid and a base? It's a salt. So an ester is kind of a salt of organic chemistry. It's the equivalent of a salt in organic chemistry. Now, esters, why do we care about producing esters with salts? Because they are very special. The esters, each ester has a characteristic smell, a good smell, a nice smell. The smells of all the fruits and the flowers are actually esters. What we smell is an ester. So esters are very important products because we use them
in the manufacturing of perfumes, of artificial flavors. And when we say artificial flavors, there's nothing toxic about the esters. So that we are used, they are used for flavoring and vegetable oils and other oils. Actually, that's just esters, like salts that are made out of long chains of carboxylic acid combined with glycerin. Anyway, so esters actually are very important in everyday life. And this way where we produce an ester from reacting carboxylic acid with an alcohol is called esterification. Esterification. So this is an esterification reaction. Let us see another esterification reaction to produce another type of ester. Say, for example, we have ethanoic acid with methanol. Ethanoic acid. Ethanoic acid would have 2 carbons. So this would be an ethanoic acid and methanol again. Let's add methanol. We get, okay, so this is the alcohol. The hydroxyl from the alcohol will combine with this hydrogen from the acid and to give us water. And give us the water. And here we'll have the ester, which is, remember, the first part is comes from the acid. Here we have ethanoic acid. So all this part, the 2 carbons and the oxygen stay there. And here, what is this part from the alcohol? The remaining of part of the alcohol attaches oxygen, which is a methyl in this case. Here we have a methyl. So there we have our ester. Remember now, the name starts from this part, the part from the alcohol, which is methyl again. So this ester will be methyl. And the next part of the name comes from the acid, which is ethanoic acid. So ethanoate. Ethanoate. So this is a methyl ethanoate. This is the name of this ester. Now, the truth about this reaction is that this is not a one-way reaction. It happens in both ways. And if we are to produce an ester, we want the reaction to move to the right-hand side. Therefore, what we do, we actually add a catalyst, a drop of sulfuric acid, for example, which has 2 advantages. First of all, makes the reaction go faster, and then it removes the water from the reaction, so it displaces the equilibrium to the right, as we want it. So there is an important aspect of we need a catalyst for this reaction if we are to produce an ester. Yes, so remember that this reaction is...
Okay, that's enough now. Okay. I hope you could hear properly because the sound was not great. Okay. Oh, brilliant. Okay. So I think that's enough for today because the time we have run out. So next week we can do perhaps another example of esterification and discuss a bit more about the reactions of alcohols and also of the acids, the carboxylic acids. Unless if you need to discuss something else as a matter of urgency, otherwise I will follow my own my own flow. Okay.